Have you ever contemplated the limitations of the computers we use today? Let's delve into this a bit. Our classic computers, while revolutionary in their time, are fundamentally binary in nature. They think in black and white, ones and zeros, with no shades of grey in between. This binary nature is both their strength and their Achilles heel. Their speed and efficiency have transformed our world, but there's a catch. They have a ceiling, a limit to how fast and how efficient they can be. And then there's the issue of complexity. Certain problems are so complex, so twisted and intertwined that our classic computers struggle to untangle them. They're like a hiker lost in a maze, going back and forth without finding the way out. These limitations have led to the development of a new breed of computers, quantum computers. So, what exactly is a quantum computer? Well, let's dive right into it. Unlike your traditional computer that uses bits, ones and zeros to process information, a quantum computer uses quantum bits or qubits. Now here's where it gets mind-boggling. Qubits have this extraordinary ability to exist as both 1 and 0 at the same time. And it's not just about doubling up, it's exponential. 2 qubits can be in 4 states simultaneously, 3 qubits in 8 states, and so forth. This special ability of qubits comes from 2 fundamental principles of quantum mechanics: superposition and entanglement. Superposition allows qubits to exist in multiple states at once, while entanglement creates a strong link between qubits, such that the state of one qubit can instantly affect the state of another, no matter the distance. In essence, quantum computers have the potential to process vast amounts of data much faster than any classical computer. How does a quantum computer work in a way that's fundamentally different from a normal computer? Let's dive right into it. The secret lies in the principles of superposition and entanglement. Don't be alarmed by these big words, we'll break it down simply. First, let's talk about superposition. Think of a coin. A regular coin has 2 states, either heads or tails. Now, imagine if that coin could be both heads and tails at the same time. It sounds impossible, right? But that's exactly what superposition is. In the world of quantum computing, our binary bits, which are either 0 or 1 in a classical computer, can be both 0 and 1 at the same time, just like our magical coin. This means a quantum bit, or qubit, can hold a vast amount of information compared to a classical bit. Now let's move on to entanglement, another fascinating aspect of quantum computing. To understand entanglement, imagine having 2 dice. No matter how far apart these dice are, if you roll 1 and it lands on a 6, the other die instantaneously lands on a 6 as well. They're entangled, meaning the state of one instantly affects the state of the other, regardless of the distance between them. In quantum computing, qubits can be entangled in such a way that the state of one qubit can instantly affect the state of another, even if they are worlds apart. Put the superposition and entanglement together, and you get a quantum computer, a machine that can process a massive amount of data simultaneously and solve complex problems that are currently beyond the reach of even the most powerful classical computers. So in the end, the magic of quantum computing isn't really magic at all. It's just the science of the very small working in ways that, while counterintuitive to our everyday experiences, are perfectly logical in the realm of quantum physics. These quantum properties enable quantum computers to perform complex calculations at an unprecedented speed. Now that we understand how quantum computers work, what makes them so unique? Quantum computers stand apart from their classical counterparts in several ways. The most striking feature is their potential to solve complex problems that are currently beyond the grasp of classical computers. They do this by leveraging the strange properties of quantum physics, superposition and entanglement. Imagine trying to find your way out of a vast, complicated maze. A classical computer would try every path one by one, while a quantum computer could explore all paths at once. Another quantum advantage is their ability to perform multiple calculations simultaneously. This is because a quantum bit, or qubit, can exist in multiple states at once, unlike classical bits that are either a 1 or a 0. This means quantum computers can process vast amounts of information more efficiently. They can sift through data, analyze patterns, and provide solutions at a much faster rate. Last but not least, quantum computers could revolutionize fields like cryptography, material science, and even medicine. Their ability to crack complex codes could make our online information more secure. They could simulate new materials or drugs, leading to groundbreaking discoveries. The potential of quantum computing is vast, and we're only just beginning to scratch the surface. These advantages could revolutionize fields like cryptography, material science, and even medicine. So, what does the future hold for quantum computing? A question as profound as the technology itself. Quantum computing, while still in its infancy, holds immense promise for the future. Imagine a world where new materials and drugs are discovered more efficiently thanks to quantum simulations. Picture a scenario where complex financial models are computed almost instantaneously, or a future where quantum algorithms help mitigate climate change by optimizing energy consumption. However, realizing this future won't be a walk in the park. There are considerable challenges to overcome. One of the biggest hurdles is maintaining quantum states. You see, quantum states are notoriously delicate, easily disturbed by external influences. This phenomenon, known as decoherence, poses a significant challenge to the practical realization of quantum computers. Another challenge is error correction. Quantum bits, or qubits, are prone to errors, much more so than the binary bits in classical computers. To make robust quantum computations possible, we need to find effective ways to correct these errors without disturbing the delicate quantum states. In spite of these hurdles, optimism abounds. Scientists and researchers across the globe are working tirelessly, innovating and experimenting to turn quantum computing from a fascinating concept into a practical reality. Despite these challenges, the potential of quantum computing is immense, and its development could herald a new era in computing technology. The quantum future is not just a possibility, it's on the horizon. And what a fascinating horizon it is.